Hello again, and this is going to be part 2 of your Monday lecture. So I have now done this in both of my classes where I've tried to record a full hour of video, and I find out my setup really only lets me do about 45 minutes. So from here on out, I'm just going to plan that every lecture is going to come in 2 parts. So that means that both classes have gotten a lecture that has started and then cut off. All right, but I do want to finish up section 20.2 in the book for today. So the last thing that we talked about was this magnetic force in terms of a flowing current. So that would be F mag, not FMG. Ugh. Let's see, FM mag is equal to the current times delta L cross B. And this is, as we said last time, not really a new equation. It's just a sum. Okay, so let's do a couple examples of how to think about this. So you're going to want to really make sure that you've refreshed on how to do cross products, both using the right-hand rule as well as the cross product expression. So there's really 2 good ways to verify direction. The right-hand rule is always an excellent choice, but sometimes as you know, I struggle with thinking in 3 dimensions, so I often will just use the cross product formula to just verify, okay, yeah, this makes sense. But whatever way works for you, the important thing is to find a method that works for you and to stick with it, and then to educate yourself on alternatives for when your method doesn't quite go as planned. All right, so let's look at a situation where we have a current flowing. So this person has been naughty. You'll see there's no resistance, so they're going to drain their batteries, which you all know not to do that. Okay, so you've got some conventional current I, so we are now full in conventional current land. Thank you, Ben Franklin. And it goes through, that's supposed to be a straight wire, so let's just pretend that that's straight. And so some section of length L goes through a magnetic field. We can see those dots right there. So your magnetic field is pointing out towards you, not down into the page. Okay, so we want to think about how we would calculate the direction of force on the segment of the wire that's in the magnetic field. So remember, we're dealing with magnetic force, not magnetic field. So magnetic field is given. Magnetic force is the cross product of the length with the magnetic field. So that's just something to keep in mind. So along the wire, the magnetic field is going to point outward from the loop. So there is a magnetic field coming from the wire. And we can see here and here on either side that that's going to cancel out. And we're going to have a net field that is pointing a net force, not field, force that is pointing down. And this makes sense for this section of wire. So we can see we've got our magnetic field B is in Z, our length of wire is in X, and so therefore the magnetic force would make sense that it would be in Y. Okay. So we want to think of this magnetic field. Man, now I'm doing this a lot. So magnetic force in terms of B, H, and L. And on your own, prove this direction to yourself. Convince yourself this is true. Never believe me. Always prove things to yourself. Okay, so for the section L, which is the interesting one, so F net magnetic is down, and so F magnetic is equal to ILB. Now in this particular case, we're just going to use the sine of 90. So we know that they're 90 degrees to each other. Let's just keep this really nice and easy. And of course, that's just equal to IBL. So when you have a wire that is going through a magnetic field and they're perpendicular, this is an expression that you can use. Now, just like our previous expression for current, This is not a new expression. It comes from just summing up several delta L's together and several moving charges together into something that is just easier to use. So a lot of equations in physics, we have our fundamental equations, and then we have it comes from a fundamental equation, and this is just an easier expression of it, and we want to use it because it is easier. All right, so we can do an interesting application of this, and we can look at the forces between parallel wires. So here we've got two wires. We've got a magnetic field that I should show you. We can see the feathers of the arrow. So this one is pointing down into the page. They have some length L, some separation D. We have the force F21, and we would also have the force F12, and they've got conventional current I1 and I2. So here's what we're going to be analyzing. Before we do that, now is a good time to talk about what an ampere is, because this is relevant. So, cool aside. An ampere is defined as the amount of current in two long parallel wires 1 meter apart. The force on one wire on the other is 2 times 10 to the minus 7 newtons per meter of length. So every meter is going to sum that 2 times 10 to the minus 7 meters per meter of length. And from this, it follows mu naught over 4 pi is exactly 1 times 10 to the minus 7 Tesla meter amps. So that's where that comes from. How cool is that? All right, so end our cool aside. And as always, prove things to yourself. Okay, so let's go back to our parallel wires. So here's the picture that we were looking at last time, and we want to look at the force from the upper wire on the lower wire. So we're going to need B1 from I1 at the location of the lower wire. And if you recall, the magnetic field of a wire is approximately mu naught over 4 pi, 2 times the current over D. This is, of course, from chapter 15 in Matter and Interactions. All right, so the force exerted on the lower wire from the upper wire. So F21 is equal to I2L B1 sine of 90 degrees is equal to I2L mu naught over 4 pi 2I1 over D. And the direction of this force is up. And once again, I want you to prove this to yourself. Okay, so we're just applying that nifty little formula that we just derived previously for this problem of two parallel wires. Okay. So moving on from this, or no, continuing with this example, this implies the lower wire is attracted to the upper wire. So now we can find F12, which is the magnetic force exerted on the upper wire. So B2 is equal to mu naught over 4 pi to I2 over D. And so this is out of the page. And so we also know F12 is equal to minus F21, so F12 is equal to I1L B2 sine of 90, which is equal to I1L mu naught over 4 pi to I2 over D. All right, so that wraps up section 20.2 and also Monday's lecture. I will see you next time for Wednesday's lecture.